Welcome to my presentation in which we'll be discussing my proposed design for a single piloted quad rotorcraft airframe. During this presentation, I hope to provide you with a brief history of rotorcraft as well as a project overview. We will take a look at the basic design aspects and specifications. We will explore the decision-making process and how the concept came to be. We will try to understand the significance of important findings and results in further detail, and finally we will summarize what we have learned. Let's start off with the introduction, in which we will take a look at the project overview, aims, scope, and outcomes in further detail. On September the 14th in 1939, the VS-300, the world's first practical helicopter, took flight at Stratford, Connecticut. This aircraft was designed by Igor Sikorsky and built by the Vought Sikorsky Aircraft Division. This rotorcraft can be seen as the first to incorporate a single main rotor and tail rotor design. Popularity exploded as adoption was almost effortless. This was further amplified as the demand for more versatile aircraft grew. Even more demanding mission types also relied on adaptability without compromising on safety or at any significant expense. Finally, other characteristics such as providing a naturally stable platform were also seen as contributing to the rise of popularity. Early designers experimented with quadrocopters as a means to address some of the underlying complexity and efficiency challenges intrinsic to helicopter design, such as to improve efficiency, as a tail rotor in a helicopter consumes up to a third of the power required for lift, just to counterbalance rotor torque generation. They also set out to address certain safety aspects, as control was impossible in the event of rotor failure. And lastly, they seek to improve and enhance control and handling characteristics. Quadrocopters, on the other hand, require constant stabilization, resulting in overloading the pilot. Power transmission to each rotor may result in increasing the overall weight and thus increasing power demand. Lastly, the effect of changes in elevation and pitch may result in reducing RPM, affecting lift. However, this was at a time when advances in computers and engineering knowledge were either non-existent or still in their infancy, and we can therefore understand why this type of aircraft was largely abandoned until now. Ultimately, the aim of this design can be seen as an attempt to marry some of the aspects found in helicopters that include being a versatile platform that is naturally stable, with a platform that would enable more mission capability while enhancing efficiency and safety. The scope of this project would include research and analysis of characteristics, technical data, and literature of similar or existing concepts and designs, to develop a design strategy to help identify and understand potential challenges and obstacles, detailing user requirements that would later be used for parameterization and specifications, after which specifications can be identified that would fulfill user requirements and be able to operate within an operational environment. And finally, the development of a concept that will satisfy user requirement and specifications. With a clear understanding of the challenges, user requirements, and specifications in mind, the outcome would result in a design of a prototype quad rotorcraft airframe capable of hovering at sea level. As helicopters require significantly more power to hover, the operational environment would only require the aircraft to hover in ground effect at sea level with no forward flight speed. A service ceiling of 3,000 meters was chosen to compensate for power losses occurring at higher altitudes. Being a prototype, a single seating arrangement would be well suited. A gross take-off weight of 380 kilograms and a cargo capacity of 30 kilograms was found to be within a good safety margin. The frame support structure will be manufactured using chrome moly, as it provides excellent strength to weight ratio, which is key to keeping weight to a minimum whilst maintaining strength and rigidity. A standard Mazda 13B rotary engine was chosen, as it was more than capable of exceeding the power demand requirements. As mentioned before, the final concept relied on the identification and comparison of unique sub-configurations first. With the requirement of a single seating arrangement, 3 unique engine technologies were identified: 4 seating arrangements, 4 rotor placements, 3 rotor elevations, and 3 drivetrain layouts. It is interesting to mention that a total of more than 1,728 different configurations would be possible with a single seating arrangement. Let's take a look at the highlighted engine technologies first. In order to understand how power requirements scaled with an increase in weight, competing solutions limited to 1,400 kilograms were compared. Comparison of gross takeoff weight to power output would provide a good estimation of power required per kilogram. For example, the Robinson R22 uses a piston engine that requires about 0.15 kilowatt per kilogram, while the MD530F uses a turboshaft engine that requires about 0.225 kilowatts per kilogram. On the other hand, the rotor engine used by the prototype would be able to provide up to 0.3 kilowatts per kilogram. The rotor engine was also chosen as it was readily available and provided more power delivery per kilogram than any other engine types. As this prototype shares certain characteristics with modern quad-rotor drones, different arrangements of the rotor support structure were identified as a sub-configuration group. Here, different rotor placements intend to highlight aspects such as the support structure and powertrain layout. Figure 9 provides an illustration of the chosen arrangement. As we can see, the support structure is similar to a modern drone. This arrangement was chosen as best suited to a shaft-driven powertrain and allowed for more maneuverability and a simplified rotor structure, saving weight and cost. Sub-configurations with respect to the rotor elevation and center of mass intend to highlight different stability characteristics. Figure 10 can be seen as a classic example of a high rotor elevation with a low center of mass, similar to a modern helicopter. This arrangement was chosen as it provided the best stability and strength, allowing for a simplified airframe layout, as well as the benefit of saving weight and cost. As we have seen earlier, investigation of competitive aircraft also yielded different seating arrangements, as can be seen in the table. As this rotorcraft requires 4 rotors, the power distribution system was also identified as a sub-configuration group. The main focus would be to identify characteristics such as equal distribution of power, efficiency, and safety. Figure 11 provides an illustration of a shaft-driven powertrain arrangement that was chosen as it provided excellent reliability, was least expected to fail, and would be more cost-effective to develop. The final concept will combine the following arrangements that will include engine type B, rotor arrangement type C, a rotor position type A, a seating arrangement type B, as well as a drivetrain arrangement type A, as previously explained during this presentation. The combination of all previously mentioned arrangements, specifications, and user requirements yielded a concept seen in Figure 12. Let's discuss the design proposal in further detail. In the design proposal, we will discuss assumptions made for the ideal flight environment, how power requirements were calculated. We'll also have a look at the forces acting on the structure and finally assumptions made relating to the design. Assumptions made for the ideal flight environment can be seen as worst case scenario with regards to efficiency and power loss. Induced power can be understood as the power required for hovering and is calculated from rotor disc loading by applying aerodynamic principles. Rotors required about 160 kilowatt at an altitude of 4,500 meters and 116 kilowatt at sea level using a takeoff weight of 650 kilograms. As the induced power requirement from the rotors is now clear, the engine power requirement can be calculated. Remembering that all of the gearboxes are 95% efficient, it revealed that the engine was required to deliver at least 186 kilowatt at an altitude of 4,500 meters and 136 kilowatt at sea level. Remembering that the theme of this project intends to focus on the frame portion alone, investigation of stresses experienced by the rotors was found to be most important as they are critical to the success of the proposed concept. Calculation of shear stresses and bending moments revealed more interesting results than expected. Maximum bending stresses were significantly larger than expected by exceeding the allowable yield stress when a weight of 650 kilograms was used. In contrast, when results of initial calculations were compared to results obtained with a gross takeoff weight of 380 kilograms, bending stresses were still found to exceed the chosen factor of safety of 2.5. After further calculation, a factor of safety of 1.312 was revealed. While the allowable stresses using a factor of safety are still within the yield strength range, results indicate that further improvements to the structure would be required. In this section, we will further discuss how well the proposed design met the requirements in further detail with regard to engine technologies, airframe layout, power transmission, and calculations. We will also discuss the general manufacturing considerations as well as looking at the associated development costs. Not only was a rotary piston engine chosen because of an outstanding power to weight ratio, other aspects such as availability and cost effectivity were also key. Figure 14 provides an illustration of the chosen engine arrangement compared to other solutions. It is interesting to note that the prototype is capable of producing 51% more power per kilogram in comparison to similar engines in its class. The rotor placement was found to be well suited as power transmission systems could be simplified with the added benefit of saving weight due to the reduction of transmission gearboxes required. It also enables the design of a rigid airframe structure which could enhance overall strength, minimalizing vibrations and fatigue on the structure and components. It will also help with the reduction of the overall footprint of the airframe structure, enabling a compact frame design, reducing the effects of parasitic drag. It will also enable the capability of placing the rotors ideally, enhancing the control and response of the rotorcraft in flight. Pitch, yaw, and roll could be controlled more effectively since rotors work in unison. The decision of using a top rotor elevation was also well suited, as it provides exceptional stability in hover and forward flight due to the weight distribution. It enhances visibility because rotors are positioned above the pilot. It also enables greater simplification and optimization of the rotor placements by allowing more freedom for design improvements without significantly impacting the layout of the airframe structure. It's also insensitive to deflections in the airframe structure during maneuvers. The chosen power transmission arrangement complements the design as the shafts and gearboxes tend to be more durable, increasing reliability. Fatigue of shafts can be minimalized by the use of carbon composites. This also enhances design flexibility of the fuselage without complicating the airframe structure design. It's also insensitive to temperature and thermal expansion at higher altitudes. In the event of failure, also enables the capability to minimize the chances of failure propagating to subsystems, and vibrations can also be minimalized and controlled to a great extent. Calculation of the shear stress and bending stresses revealed more interesting results than expected. When a gross takeoff weight of 650 kilograms was used, this revealed maximum bending stress was significantly larger than expected by exceeding the allowable yield stress. When results of initial calculations were compared to results obtained at a gross takeoff weight of 380 kilograms, bending stresses were still found to exceed the chosen factor of safety of 2.5. As it was found, more development with regards to the airframe structure and material selection would be required in order to reach the intended design factor. Manufacturing techniques will rely on guidelines provided by ISO with respect to joining, machining, and so forth. This design was approached from a practical perspective with simplicity in mind, with the goal of being as cost-effective as possible. Most of these components do not require highly sophisticated equipment to manufacture and can also be bought over the counter. It is important to remember that the joining of chromoly parts would rely on the use of TIG welding, as any impurities could result in structural weakness. Finally, if we get to the costing, we look at the material cost to be 15,000 Rand, components in excess of 45,000 Rand, machining, which was estimated at 600 Rand per hour, comes down to about 230,000 Rand, with labor at 130,000 Rand for a total of 420,000 Rand. In conclusion, the prototype meets all of the criteria as detailed in the design specifications and user requirements. It is important to mention that the power requirements were exceeded by almost 20%. Also, the gross takeoff weight was found to be 1.7 times lower than the initial assumed gross takeoff weight of 650 kilograms. Calculations that however reveal that the further development of the structure would be required, as the intended factor of safety barely even held when a gross takeoff weight of 380 kilograms was used. However, a reduced power demand as a result of a reduction in weight and excess power the engine can provide, the addition of extra supports would be possible as is planned for the second iteration of this prototype. Thanks for taking the time to listen to my presentation. Please feel free to email me with questions or if you require any other information.